Yesterday we have started discussing about the classification or the types of aquifers that we encounter in groundwater. We define aquifer and explain the definition as a geologic formation that can store and transmit water to wells at economic rates and under ordinary field conditions. Example, you have limestone aquifers, sandstone aquifers, and then we have other geologic formations like aquitard, aquifuge, which are usually semi-impervious or impervious, completely impervious strata. And all these aquifers and aquitards, they play a role in formulating boundary conditions. That is when talking about the modeling aspect. We have taken time to explain in detail this particular and renowned figure, which we all know right from our first introduction to hydrology or groundwater hydrology. Here what we did was to explain what is confined aquifer, what is unconfined aquifer, and then what are the inherent properties or characteristics of each one with respect to water availability, pressure head or piezometric head. And we said so many things about that. And today I hope to finish with this particular slide, which it was planned for just one lecture. And now this is, I think, the fourth lecture. This is the fourth lecture. It was planned for just one lecture. But this is the fourth lecture that we are discussing this particular slide. Hopefully, this morning we will be done with it. And if time permits, probably we can move on to the next one. So, in the previous slide, we defined aquifers. We classified aquifer in terms of the presence of impervious boundary above or beneath, where we have confined and unconfined. Now, aquifers are also referred to in different ways. One, you can define it according to the type of material of which the aquifer is made. For example, that is the particular geologic formation. Okay, and when I say geologic formation, most of you have done geology for engineers, whichever school you graduated from, at least as long as you study civil engineering. So you must have studied geology for engineers, okay, where the properties of rocks were itemized and explained, isn't it? Yes. Because soil is as a result of weathering of rocks, isn't it? Over time, due to wind action, water action, and what have you, they now get transformed into different types of soils, be it clay, silt, gravel, and what have you, okay? So all these constitute the solid matrix of the porous media or of the aquifer. So they can be classified based on the particular geologic formation present. Like we may speak of sandy aquifer. It means the aquifer is made up of sand. We may speak of limestone aquifer, sandstone aquifer, okay? That's referring particularly to the geologic formation that constitute that aquifer. Also, it can be classified according to the geological age of the layer. Example, we have Pleistocene aquifer. This is usually referring to the geology, okay, the geological part, according to the age of the layer. And then it can also be classified according to the local name given to the geologic layer, like Zaria Aquifer. We have Zaria Aquifer. Do you know that? Huh? You don't know? Despite having taken, where do you learn geologic survey? I think it's still in hydrology, right? 543.
Water supply.
What? Water supply. So, haven't learned the geological survey and what have you, still don't know the aquifer that is feeding you. It is called Zaria Aquifer. So you can define or classify aquifer based on a local name. Okay? But Zaria Aquifer probably is underlain by basement complex. Okay? Basement complex are usually carbonate or granite rocks, okay, which may not be good aquifers. But nevertheless, like I said, probably if you go to geology, you may have interesting findings, geologic surveys about the immediate environment, Zaria, and even other areas of interest. Okay? Because if we have something like this with the characterization of these aquifers, and then using our background knowledge of which one will be good aquifer and what not, then when sinking any borehole, we can know exactly, for instance, the depth to which we are going to hit a particular confined aquifer, so that the reliability and sustainability of that particular source is ensured. Okay? But like I said, probably in one of these days I may, although I don't know anybody in geology, but I may go there and try to find out what they have. Okay? Now it can, this we already explained, according to the presence of confining layers, where we defined it as confined aquifer bounded above and beneath, unconfined bounded from below, and perched aquifer and leaky aquifers. Perched aquifer, the one, it's found in the unconfined zone. You know, when you have an aquitard, then it will appear as if it were a pond. Okay? So it's more or less like temporary, not really continuous aquifer. Okay? And leaky aquifer, in which it leaks to adjacent aquifers. All these classification, when we come to the modeling proper, they have implication. As I mentioned before, they have implication on formulating the boundary conditions, because each one of them has different boundary conditions. And by boundary condition, as the name implies, you are simply describing the boundary. Simple. You are simply describing the boundary in terms of flow, in or out. Simple. Okay? But then these are some of the most important input into any model. They are some of the most important input into any model. The boundary conditions have to be clearly and well defined. Okay? Later on, we will move into the boundary conditions, and for those taking, although we haven't started, the advanced mathematical modeling, which is the mathematical methods, that is where probably we will go in depth into the formulation and the computation of the boundary conditions. Now, yesterday I asked you this question: what is episometric surface? Then someone was trying to explain. I said, okay, don't worry. I will not take so much time, because tomorrow we will dwell on that. And God so kind, we are all here witnessing today. So let's start with that. What is piezometric surface? Yes?
So rise the head of water against the atmospheric pressure.
What?
Rise in the head of water, or surface of water. Surface of water that rise against atmospheric pressure.
Against atmospheric pressure. Yes?
It can be simply defined as an imaginary line, and so the eye through the water will rise if an episometer is inserted
Through the?
into the water.
Into the water.
And it can also be defined as the summation of the velocity head and the pressure head.
Velocity head and pressure head. That's the mathematical formulation, definition, isn't it? As the sum of velocity head and pressure head, yes?
Height of water in the piezometer is mathematically defined as the summation of all the heads vertically.
All the heads?
Yes, that is pressure heads, data.
Including velocity head, right?
Yes.
Any other definition?
Simply piezometric surface
Mm.
is a rise of water level in confined aquifer.
Now, the mathematical definition, do you agree with their definition? What about you? You don't know. Oh, yes or no? He doesn't know. Yes, what about you? You agree with him? What? No. You don't agree? Then what is your own version?
I think the piezometric surface is just the height of water equivalent to water in a confined aquifer.
Then the mathematical formulation, yeah? Mathematically defined as what? Oh, yes. Anything? Did I do? But you all failed. Fortunately, you all failed.
Pressure divided by...
Yeah, I agree with the definition as in, okay, is the imaginary line or the height of water in unconfined aquifer, okay. But the mathematical definition is wrong. Someone mentioned is sum of all the heads. Someone specifically says is the pressure head plus the velocity head, which are all wrong. It is the elevation head plus the pressure head that constitute the piezometric head, because we measure it with respect to a datum. So that gives the elevation head. And then we have the pressure head. That's the particular height of the water, isn't it? When like a piezometer is inserted or whatever it is. Okay? This is what we call the piezometric head, isn't it? Because this is the height of water. So if you insert a well, it will rise up to that level. Okay? But of course, we have a datum. Okay? So you have the pressure head and then the elevation head. Okay? This is RAIN 201, our basic fluid mechanics, right? Now, piezometric head is defined as potential energy per unit weight, also referred to as elevation head Z. Pressure energy per unit head or pressure head resulting from the pressure in the fluid. It is resulting from the pressure in the fluid. In a 3D porous medium domain, the piezometric head varies from point to point in space and in time. Okay? It varies from point to point in space and in time, meaning it has temporal and spatial variation. As such, the piezometric head H can be given as, or is a function of x, y, z, that is the spatial variation, and t, which represent the temporal variation. We say it varies in space, and you may see this as if it were a straight line, isn't it? Meaning it wouldn't have probably spatial variation, but it is not really like that. It varies as you move on, okay? And also it changes with time, because if you have high amount of recharge, it changes, isn't it? Except that for the unconfined aquifer, the changes is more pronounced in the unconfined aquifer than in the confined aquifer, okay? That is because of the impact on the water table, which is usually experienced by the unconfined aquifer. And we have explained that that is different from what we experience in the confined aquifer. So the piezometric head is a function, it varies spatially and temporally. Although here we have started introducing X, Y, Z, T, and that is the modeling aspect, in which later on, like I said, after this, we will take the next presentation. After that, we will go and review vector algebra. The vector algebra we are reviewing is nothing different from what you did in Math 106. I think it is also called vector algebra, right? Yeah. So that was what we are going to review, because ultimately we are going to be expressing, and also you did this course. What is it called? I think 342. 342 mass 342, right? The partial differential equations.
ODE.
No, not ordinary. Ordinary you did in 341.
341, yes.
Yeah.
That's interesting.
342, that's when you start introducing del, the partial differential. I'm not referring to the ODE. I'm referring to the partial differential. Del y by del x, right? That's function of several variables, isn't it? I started telling you before when introducing the concept of the groundwater modeling. More often than not, you do it in one dimension, two, up to three. Because practically speaking, almost everything is in 3 dimensions. Okay? But for simplicity, you start from simple to complex. So 1D model is oversimplified because it will ignore a lot of things. For every model you must have what is called the underlying assumptions, which guide the formulation of the governing equation. And also those assumptions will in one way or the other eliminate some factors, some variables affecting the model in order to simplify it. This also we are going to look at it, okay? So through that, we may have 1D model, 2D, and then the all-encompassing, which is more realistic, is the 2D. But still, you may have excellent 2D models which can approximate the system and whose performances probably has been tested and they do well, even under field conditions. But the 3D one is the one, that is depicting the real scenario, except that it is more complex and its solution will be also much more complex to analyze and arrive at. Okay, this we will explain once we start introducing the modeling processes. Okay, now the piezometric head is given by H equal Z plus P over rho G. That is exactly what was defined by one of you yesterday. But then this morning, all of you have forgot. That is the elevation head. P over rho G is the what? Is the pressure head, isn't it? It is the pressure head. P is the pressure in the fluid, and then rho density of water, G acceleration due to gravity, and the pressure usually expressed in the unit of pressure for P, either Pascal, Newton or kilonewton per meter square, and what have you. And then H is now in meter or as height, L, dimension L, isn't it? This is very important because most of the modeling aspect as it affects the groundwater modeling will be trying to find the variation of this head, spatially and temporally. At the end of it all, we want to see how is the head varying. This particular surface, the piezometric surface, how is it over time? We'll try to have some wells into the particular aquifer, pumping at certain rates over a given amount of time, and then try to see how will that pumping rate and how will that number of wells that we have affect the piezometric head over time. Do you understand? If you remember when introducing the groundwater modeling in my first class, this is what I told you that the groundwater modeling is mostly about, in the sense that you have a lot of wells tapping from a particular aquifer. You want to determine the rate at which the aquifer will not be adversely affected. And when we say adversely affected, in this case, more often than not, we are talking about the piezometric head. Because it will be adversely affected if the piezometric head goes down. It means you are depleting the aquifer in no time, isn't it? But if it stays relatively, the depression is something manageable, and then, you can now go ahead with that pumping rate. Otherwise, you may have to review the pumping rate so as not to affect the aquifer adversely. But remember, we mentioned the quantity and quality in the sense that once you are drawing water from an aquifer, the quality is also invariably affected. So the two must go hand in hand. So in the first part of it, when discussing the modeling part, we will look at the groundwater modeling aspect proper, in the sense that we are going to use ModFlow. Probably you all know ModFlow, the software, okay, in which we will have some hypothetical aquifer or situation in which we have an aquifer, we have pumping well, recharge, and all that at a particular rate, and then run it to see how the head, is the piezometric head, how is it going to be affected over time. And then from there we move to the other part, which is the contaminant transport. In a situation whereby you have a contaminant, for any reason, it can be accidental discharge, it can be deliberate discharge from industries, it can be leakage from underground storage tanks, which all happens every now and then, isn't it? That may find its way into the groundwater, be it the surface water, or the unconfined or the confined aquifer. Now, in that case, when you have a contaminant dissolving in your groundwater, now how do you now understand the transport processes? How does it affect the movement of the water in the groundwater? How does it affect the groundwater movement? And how can you model the concentration as it moves along? So that will be the second part, which we will briefly discuss and see how that can be done, because it will change the hydraulics, of course. The hydraulics will be affected. So we will see how it affects the hydraulics of the groundwater and how it can also be modeled. By modeling here, if you have a contaminant here, let's say this is the direction of groundwater. How much time will it take for it to move from here to here? Because groundwater moves very slowly. Probably, usually, you can find it 0.2 meter per day. So you can imagine, 0.2 meter, that's like 20 centimeter per day. 20 centimeter, that's like this, per day. So it moves at a very, very low velocity. So now, if you have a source of contamination here, and you have a well, so with the model now you can determine how long will it take for the contaminant to travel to this point. And you can predict over time what will be the concentration. If at time 0, the concentration of the contaminant here is so amount, C0, what will be the concentration here after a given amount of time? So that you can now think of a proper remedial action, a proper clean-up strategy that you can use or you can put in place to remediate the aquifer. That will now take us into something else, the remediation of groundwater. Although we may briefly talk about it, but then for those at the PhD level, you have a course, I think, bioremediation now, but probably to be changed into remediation so that it is more encompassing. But even for those in hydraulics, which most of you are, you may say you are just interested in the first part, when you have wells, the rate, and how it affects the piezometric head. But still, when there is contaminant, you still need to understand how to model it. You won't say, no, this is where my job stops, and once there is contamination, I have to invite an environmental engineer to come over. No. You have to understand the dynamics, the hydraulics, and then anything to do with the computation, the contaminant modeling processes. And that will slightly take you into the environmental engineering part about the characteristics, the properties of these contaminants once they are inside the porous media, and the transport processes and mechanisms. But still, and that is why, like I mentioned previously, sometimes you can separate water from environment completely, sometimes. But in some respects, more often than not, they go hand in hand. In a particular problem, water sometimes may have greater percentage than environment. In another one, environment could have greater percentage than water. And that is why, like, even the program is structured in such a way that, the first semester you take courses all together, both in environment and water. So that whenever there is, for those in hydraulics, whenever there is an environmental issue, they wouldn't say, no, I'm not in environment. At least you have some basics, some basic information to, start with. And the same thing for those in environment. They wouldn't say, no, I'm not in water, so anything to do with hydraulics, I'm blank. No way. You also have to have some particular foundation in that area, because more often than not, they interact. All right. So with this, I think I have introduced the piezometric head, although, like I said, we are going back to it. This is just to define it, and then later on, when we start the modeling proper, it will be one of our main output to see the variation of the different processes taking place in the aquifer on the piezometric head, which we say it varies temporally and spatially, isn't it? And like I said, later on, we are going to review our vector algebra, because this x, y, z, t, and what have you, we need to go back to vectors, because once you have 2 dimensions, 3 dimensions, then it's better you convert everything to vectors. It gives easier way to manipulate and treat them. You have to come, and most of the variables that we have, you will realize that they are vectors, or they vary spatially and temporally. And once you have this, then you will have to convert everything to vectors for easier manipulation. Okay? When we get there, we will expatiate more on that. This is just like introducing that particular aspect. And then we'll move down to the last. We have capillary pressure. You see, now we have started discussing about pressure. If you remember yesterday, some of you were talking about pressure. I said, don't worry. We are going down to pressure and try to review all that has to do with pressure. Okay? From pressure head, piezometric head. Now, we also have something called capillary pressure. In the unsaturated zone, you have solid matrix, okay? Grains, isn't it? And here you can have water, okay? This is water, this is air. This is the porous media, the solid matrix. Okay? Water here is called the wetting fluid, and air is called the non-wetting fluid. Okay? Water, of course, is wetting due to the... Why does water wet glass or wet anything? Can you tell me? Why do we call water a wetting fluid? I mean, why does it wet substance, be it glass or whatever it is? Why is that so? Because of density. What about it? Because it is hygroscopic. Hygroscopic, right? Hygroscopic. I remember hygroscopic, effervescent, and what else do you call those names in chemistry? But hygroscopic, it means it absorbs moisture from the atmosphere, isn't it? Like most of the salts you have, calcium carbonate, this and this, they are all hydrated salts because they absorb moisture from the atmosphere. So that is what is called water of crystallization. So you have calcium sulfate, .10, O2, O4 water of crystallization. And that's why most of the salts, you see them under tide, because more often than not, most of the salts, when you put them you know, when you expose them to air, they absorb moisture. So water, hygroscopic, I mean, the two doesn't match. Why does water wet glass? This is SS1 question.
Adhesion. Because of adhesion. Because of adhesion.
What?
Because of adhesion and adhesion.
Force of
Adhesion is
cohesion and adhesion.
between water and glass.
So which one is which? The
Adhesion force.
oh. I think I will need to ask you to go back to your SS1, review your chemistry, review your physics, your mathematics. I will start from the university level. But your SS1 physics, your SS1 chemistry needs to be thoroughly reviewed. Thoroughly reviewed. Because all this, you know, all these questions fall on, you know, SS1 physics, isn't it? Is it because of what?
It is because the adhesive force is...
No, I was thinking you will tell me why you are not, as if you are not remembering those basic aspects. I was thinking you are going to provide reasons.
No, I wanted to provide the answer.
No, I want answer to why you are not remembering those basic principles in your SS1 physics, SS1 chemistry. That is my main question, because I will keep on asking you questions. In fact, today we'll also have another quiz. So, questions will never stop coming from my side. Never. And most of these questions are basic. Either basic as far as SS1 physics, SS1 chemistry, or basic as far as your first course in water resources, fluid mechanics, REN 201. All this is, you know, from REN 201, isn't it? First course in fluid mechanics. So maybe I will ask you to revise your physics, SS1, physics, chemistry, SS1, and then I will come up to say you will revise all your mathematics. Your mathematics, although here we may not go into math, but in the other course, up till now you didn't come, so that we agree on the time for 901. Okay. Because if I don't have any confirmation about the time, then next week's our class will not start next week. Because I need time to prepare. So you may also have to revise all your fluid mechanics courses from REN 201, 301, 302, 401, 501, and then 503. Okay? Because all of these are basics, isn't it? Now, so you are telling me the reason why it waits.
Why water wet glass? You know, there are two forces that act in a fluid. The adhesive force and the cohesive force. And the cohesive force is the force between liquid of the same molecules. While the adhesive force is the force between liquid of different molecules. If the cohesive force is more than the adhesive force, then the molecules of this particular liquid tend to band together. And that is why mercury does not wet glass.
No, I'm referring to water now.
The water, the adhesive force is greater than the cohesive force. So the particles tend to, that means the force of between the two different substances is greater than the force between the water molecules.
Okay.
So therefore, the water wet glass. That is the reason why water wet glass.
Okay, good. So I hope now we are cleared. We are given a brief review on that, right? Why water wet glass? Okay. I'm still back to wetting fluid, because I asked you, why do we call water a wetting fluid, isn't it? Like I said, one thing with modeling is that the time for memorization, for cramming, for crashing, for memorizing equations and formulas, that time is gone. Now it's time for internalizing all the theories you know before, all the formulas. By internalizing, I mean by understanding every bit of it. Knowing what it is and what it looks like. Something that if asked to describe, you can vividly present a good picture of it. Because that's the only way you can now model that process correctly. If you don't understand the processes affecting the system, then of course, when you come to formulate your model, you will do away with so many variables affecting the model. And that is the beginning of a catastrophic model. Okay? And that is why we are going this, I don't know if I will say this depth or this surface, because to me all these are bases, so it is like on the surface, but except that for everyone there is no assumption that you just know it, so I will just explain and move on. No. I will have to ensure that you know it and you understand it correctly before I move to the next aspect. Because and that is why, like I told you, if there is anything you have question that is not clear, please pause and then ask questions. Okay? Don't just assume, okay, this I understand. Okay, when I get back home, I will sit down and look at it the second time, and then I will get it. Okay? Because that's one of the secrets to learning. That's why you are all here. If there is anything that is not clear, don't let us move out. Bring my attention to it and then ask whatever question, no matter how elementary it may look like. Don't mind. Okay? Now, we have wetting fluid and non-wetting fluid. The capillary pressure is usually referring to the pressure difference between the non-wetting fluid and the wetting fluid, which we designated as PNW non-wetting fluid, PW wetting fluid. Okay? So in this case, the capillary pressure, when you have air and water, we can have it air-water interface. Okay? So it's now the pressure difference between air and water. Okay? And this usually refers to the unsaturated zone, because although it can also refer to the saturated zone, but in that case, this one will be zero because we don't have air in the unsaturated zone. Sorry, in the saturated zone. We only have water there, isn't it? But in the unsaturated zone, you have the two coexisting, isn't it? You have the two coexisting together. Okay? We will not say much about the capillary pressure now, but when we'll start to talk about the contaminant transport mechanisms, we may come back and add more on the capillary pressure. Okay? What?
That means that the capillary pressure at saturated zone is negative.
At what?
At saturated zone.
Yeah, it may be negative, but then when you formulate the pressure equation, you have P over rho G P over rho G plus H equals constant. Okay? Equals constant sometimes. And then at the end, I don't think I caught this correctly. You will have P1 equals rho GH minus plus P naught. Depending on the boundary condition, this may be zero if it's atmospheric, because we take it as the reference pressure, isn't it? Although in actual value, the absolute value is not zero, but we make it zero so that we can measure pressures above and below the atmospheric pressure. So you find out that the pressure is usually minus rho GH. The minus sign has meaning. The meaning is that the higher you go, the lower the pressure. Okay? That is the meaning. So that when you insert, when it is 0, this negative will cancel with this and it becomes positive. But like I said, we will deal with it more when we reach the contaminant transport processes. That's when we'll bring back the capillary pressure. Okay? But for now, it's just to introduce to you that there is another pressure called capillary pressure, which is giving us the difference between the non-wetting fluid and the wetting fluid. Okay? I have started mentioning about atmospheric pressure, and we talked about atmospheric pressure before, right? And then just now, I just finished mentioning about REN 201, right? And now we have just how many concept quizzes? Just 2, right? And they are very simple and straightforward, direct. They said, how are the following parameters related? Just like we did for the first one, like one equation having all of them, okay? Most especially for the first one, piezometric head, pressure head, and HGL. What is HGL? What is it? Hydraulic grade line, isn't it? Hydraulic grade line. I'm sure you did this in 501. Very well. And even in 301, 302. Hydraulic grade line. Okay? So, how are these parameters related? Like I said, we are now talking about pressure. We started with piezometric head. We first started with atmospheric pressure, right? Before, in our second or third lecture. Now we came down to piezometric head or pressure head, and then pressure head, and then we talked about the capillary pressure. And now we want to know, for the first part, how is the piezometric head, pressure head, and hydraulic grade line? How are they related? No interaction, no interaction. How are they related? That is number one. Number two, going down to fluid mechanics, REN 201. You remember what is called gauge pressure? Gauge pressure, absolute pressure, and then we have atmospheric pressure and vacuum pressure. You will come back, we will have this quiz with you. So these 4 types of pressures, how are they related? The first one, probably you can tell me just one equation or so, and you may have all of them. The second one, okay, if you know what you are doing, then let's see how you answer the question. Let's move on. Quiz number 2. So start writing. Are you done? It's a very simple question, by the way. It's just testing your ability to recall this, because like the first one, I just finished explaining, right?
Yes.
The first one, I just finished explaining. But I only introduced another thing called the hydraulic grade line, which you must be aware of, isn't it? Okay? Like if those in 200 level will see this kind of question, they will just laugh and say, so is this what they do at MSc? It means I'm already an MSc holder, isn't it? Because I can do this, I know the answer, so let's see how you respond. You have 3 minutes. And like I said, that's why, like this one, this is a concept quiz, testing your understanding of the basic concepts. Basic concepts. Okay? You have 3 minutes, starting from now. But first, try to internalize them. Try to understand this. I'm sure you did gauge pressure, isn't it? In 201, absolute pressure. Here we did atmospheric pressure. And then you can tell me also about vacuum pressure. If you are done, you can draw my attention so that I can. 3 minutes is gone. So can I start checking around to see if you are done? Or you are still deriving some complex differential equations here and there? Don't look back. Look at your work. Who has finished? Anyone? You see, all these are the different pressures we have, and that in one way or the other affect our system. So I will not just come and assume that you know all this and just move on. No way. I have to ensure that, yes, even if you forget, okay, we can remind you, but there is no assumption. I mean, we don't assume that everything is just cozy. We have to test and make sure that, yes, you can exactly recollect all these basic parameters. Okay? Yes, yes. This is 4 minutes and nobody is drawing my attention to come and check what he did. Done? Okay, good.
Not done.
I saw you.
Partially done.
Okay. So the first one, A. No. This is the first one, right?
No. Yes, this is the first one. Starting from here.
But there's no pressure head here. It's absent. Where's pressure? Oh, sorry, pressure. Then what about piezometric head, HGL? Which one else?
This.
Piezometric head is missing.
This piezometric head. This also pressure head. This piezometric head.
No, this one I'm trying to this.
This piezometric head.
Piezometric head.
This pressure head equation. This piezometric head equation. This pressure head equation.
Piezometric.
This pressure head equation. This is a hydraulic grade line. This plus this.
Then what about the absolute pressure?
The absolute pressure is this gauge and this one.
What is at pressure? Atmosphere?
Yes.
Then vacuum pressure?
Is this one? I forgot what is vacuum.
I've forgotten this one. Done? You have to be fast. Tullah. All of you are in hydraulics, am I right?
Yes, sir.
Is there anybody in environment here? Nobody, right? So I'm in the right class. I didn't miss my way, isn't it? Yes, yes. Done?
No.
Then the A part. Wow. Done? Gauge pressure. This is the A part?
Yes, sir.
No, but you didn't relate them. You are justifying giving me some equations for each one. You didn't relate them. Like how is pressure head, piezometric head related to HGL? Can they be combined in one equation like that? Not just to give me. Attempt.
This one.
Give me some equations. I don't even know. Why don't you use?
This is a Episometric. This is the formula. This pressure is the hydraulic grade line is a pressure P square over T times plus Z. That's all. Then since this
What is this?
P pressure P square over Y.
What about you? This absolute?
No, I'm trying to get the second one.
AP. Both on the same side, right? Sorry, on both sides.
It's wrong.
Okay.
I'll try to.
James. Project head was row GH. So using this one as to see the P here row GH. So elevation head is what? Z+.
So now HGL plus this equals that. Yes. What? What have you done? You must do something. Gaskiya mene?
The hydraulic grid line is the height from the deck to
And how are they related? Piezometric head, pressure head. Not just to show me.
the equation that relates
Which one?
V plus rho G, the pressure over rho G.
Yeah, show me everything up. Which one is piezometric head? Which one is pressure head? Which one is
This is the
HGL?
piezometric head, while
Z is the piezometric head?
that's the elevation.
Yes. No, not different. Okay.
But what relates them together is road. That's
Relates what? In what way?
because all of them have to do with acceleration due to gravity.
Ah, yes.
But all I said is the first one that they are all affected.
What?
That's the first one.
Yeah.
They're all affected by atmospheric pressure and gravity force.
Then the equation. I said, how are they related? Any equation or relating them?
The equation that don't bring us.
Ah, then you are blowing English here. What?
The A part.
The A part.
The piezometric head, this is the pressure head. So this is how they relate to this hydraulic.
Yes. Class rep. Class rep must get it. All right. I think I'm in the wrong class. Am I not in the wrong class? So what do we do? Because it seems most of these basics are off your mind, your memory, your understanding, and what have you. And you can't move forward without them. You can't. And like I said, they are simple things, very simple, and very basic and elementary. Some of you got some of them right, or some of the answers right, but most of you didn't. And that's why I asked, am I really in hydraulics? Those majoring in hydraulics option. Because if you are majoring in hydraulics option, then there is no excuse. You don't have any excuse why this simple relationship, will not be there in your mind or in your memory. Okay? All right. I will explain them, but what it means is that you have a lot of work to do. Not on the advanced formulation, but on the basic aspect. You need to go back and review them. Because all this will, in one way or the other, affect our input into any model that we are thinking about. And like I said, if you don't understand how they are or how they are related, you will be interchanging them unknowingly. You will interchange pressure head with piezometric head, which is 0. And then you will go on and run your model. And then, it is not acceptable that you will be found wanting in some of these basic aspects. But like I said, nevertheless, we will still go as low as it takes to review them and then move forward. Okay? I just finished explaining the piezometric head, isn't it? But even that, some of you didn't get it right, because we said piezometric head, It is here. It is just in the previous slide. Piezometric head is defined as H equals Z plus rho GH. And we said the pressure head is what? P over rho G. So the first thing I should expect to see is the piezometric head is equal to Z, elevation head plus pressure head. Simple, isn't it? Piezometric head is given by elevation head plus pressure head. Because that's what I just explained here. Okay? Now, that's the relationship between pressure head and piezometric head. What about the hydraulic grade line? How is it related to any one of, to either the piezometric head or the pressure head? Can anybody say something?
The hydraulic grade line is basically what transpires in the fertilizer.
No, not definition. I don't want definition.
Which is
just related to pressure head and piezometric head.
Piezometric head plus losses.
The hydraulic grade line?
Yes. Hydraulic grade line is the piezometric head plus velocity head.
Hydraulic grade line? Oh. Then, before my next class, it is compulsory upon all of you to go and review your REN 201, REN 301, and the first few chapters of REN 501. Because definitely you all pass them and then threw all the knowledge aside. You might have scored A in those courses, but now is the time to use the knowledge derived from the courses. And that's why, like I told you, here nobody will be mandated or compelled to memorize anything. But all you need to do is to understand. Simple. The hydraulic grade line is synonymous to the pressure, the piezometric head. Simple. They are one and the same. We either say hydraulic grade line or piezometric head, which is given as the sum of the elevation head and the pressure head. The total head is the one that has what? In addition to the elevation head and pressure head, it has what? The velocity head. And this is what we do in REN 201, isn't it? Bernoulli's equation. The energy conservation, or either 201 or 301, because you start probably in 201 and continue in 301 and even probably 302. The hydraulic grade line is the piezometric head. The same, one and the same. We either call it hydraulic grade line, in another textbook we call it piezometric head. Simple. And then each one of them is equal to the elevation head plus the pressure head, which is what we explained before, isn't it? So, you have to be very attentive. Because, like, the pressure head and the piezometric head, I explained in the previous slide, isn't it? So, at least I should expect 100% of you to get that one right, isn't it? But still, some are mixing them up left and right, you know. Yes? Yes.
I was looking at the situation. What we are actually looking for is a situation where the pressure head, the piezometric head, the HGL are combined.
Yeah, they are all combined in one equation. Simple. HGL equal piezometric head equal, let me use this piezometric head equals elevation head. Let me use H elevation plus pressure head. Is this not an equation? Isn't it? The HGL is equal to piezometric, is equal to elevation head plus pressure head. So if you give me this, you are right. So that's why I said, how are they related? So yes, there exists one equation that relates all of them. Do you understand?
Yes. Sorry. What you
What?
What confused me was...
What?
What confused me was...
Okay.
You talking about balance equation. I can remember the diagram we have there that has to do with the total height. They use the mathematical expression. They use P all over Y, not P all over W or P all over rho G. So that Y, are you saying Y is the same thing as rho G or W?
Okay, not Y.
It's gamma.
Gamma.
It's gamma they use. It's not Y. Gamma. Gamma they use. And it's the same thing as
So,
omega.
did you see why I asked you to go and review your 201 and 301? Because it's never Y. It was never Y that was used. It was gamma. And gamma is the unit weight of water, which is the first thing that will be taught in 201 as the properties of water. Surface tension, unit weight, this and that. Okay? Now we go to the next one. Is this one clear? You see, this pressure head, pressure in particular, like I said, it plays important role in our modeling. It will be like the major output that we'll be looking after. So, you have to understand it very well, right from the beginning, ab initio. Yeah.
What about the energy grid line?
The energy grid line. I should ask you that. Thank you for raising that question. So what about the energy grid line? The EGL. I should have added EGL here. EGL. How is it related to the rest?
You now add those solutions to the velocity.
So it's equal to the piezometric head plus velocity head. So the energy grid line is equal to the total head. It's the total head. And when we say the total head, you have the elevation head, the piezometric, the pressure head, and the velocity head. And that is what is referred to as the energy grid line. Isn't it? So, I hope you have now been, not upgraded, because this is something, you should have known in your previous courses, isn't it? But probably you forgot them, or now you are not using them. But I'm sure some of you are teaching these things. You guys, are you not teaching this to your students?
Yes, but you have to.
And that's why I'm asking all of you to go and review your fluid mechanics. Okay? Now, let's move to the second part of the question. Gauge pressure, absolute pressure, atmospheric pressure, and vacuum pressure. Most of you got the relationship between atmospheric, absolute, and gauge pressures correctly. In the sense that they wrote P absolute equals P atmospheric plus P gauge. Okay? Yes. This relationship is correct. Although some of you maybe missed the sign, maybe they put minus, but most of you got this, that the absolute pressure, if you remember, we talked about atmospheric pressure in depth in our last two classes. Now, the pressure at a point is referred to as the absolute pressure. It can be atmospheric. In that case, you don't have any gauge pressure. The gauge pressure is 0. It can be only gauge pressure, no atmospheric. It can be both. The pressure in your tire is gauge pressure, isn't it? But if you want to know the total pressure, which is the absolute pressure, because the gauge pressure is the pressure above the atmospheric pressure. It's the pressure because you introduce more air, the pressure in your tire is higher than the atmospheric pressure. By what? By this amount, by the gauge pressure. Do you understand? But then, back to the gauge pressure. Is it always positive? Like I said, you see, whenever you come to my class, you will expect probably I may ask you like 100 questions. And these questions are not some complex questions per se, but there are things you know. From those things that you know, they are the ones I will now explore more and more and more. Simple. just to make sure that you understand them correctly. So, the gauge pressure, is it always positive? It can be negative. You sure? So it's not always the pressure above the atmospheric, it can be below the atmospheric pressure. Isn't it? But more often than not, it's positive. But if it is below the atmosphere, because it's the excess pressure above the atmospheric pressure, isn't it? Given by this equation. Then if it is below the atmospheric pressure, what do we call it? What?
It is vacuum pressure.
Vacuum pressure. So, vacuum pressure, the vacuum pressure is negative gauge pressure. That's how they are related. Simple. The vacuum pressure, because the vacuum pressure is always positive. So it's just like the absolute value of the gauge pressure. If it is negative, it's now vacuum pressure. Although sometimes the pressure in the vacuum is assumed to be zero, so it's taken as reference. But when you have negative gauge pressure, it is called vacuum pressure. Okay? Now, let's see how to relate all this together. This is the same famous diagram that you know, pressure relations, piezometric head, pressure head, and HGL and even EGL. You have water flowing, okay? You have the elevation head, the pressure head, the height to which water rises within a piezometer, and then the velocity head. And then this is the total head, which remains constant throughout, according to Bernoulli's equation, isn't it? Okay, so the pressure head is here. The piezometric head, you add the elevation head, isn't it? This is the piezometric head. From here, this is the piezometric head, isn't it? And then the hydraulic grade line is also the piezometric head, right? Because in that case, you can like connect lines, okay, and it gives the hydraulic grade line, isn't it? And then the total head, or the energy grade line, which is now this line, which is constant, according to the Bernoulli's theorem, right? Which includes the velocity head. This is what we have in REN 201, REN 301, isn't it? Am I right? Now, the other one, gauge pressure, absolute pressure, atmospheric pressure, and vacuum pressure. If we have a reference pressure, let's say it's zero, absolute is zero. When absolute is zero, it means the atmospheric and the gauge pressure are all zero, isn't it? So, we have a reference line. On this line, all are zero. All the different pressures we have, zero. When you move up, this is atmospheric pressure, isn't it? 101 kilopascal, isn't it? At this level, you have local atmospheric pressure. And it serves as the reference pressure for the gauge. Because the gauge is giving you the pressure above or below the atmospheric pressure with respect to the atmospheric pressure. And that's why here it's written gauge reference point. Is that clear? So here, the gauge pressure is zero at the atmospheric level, isn't it? The gauge pressure is zero. And then, yeah, this is the gauge pressure. And then the absolute pressure is what? It's equal to the atmospheric. Because gauge equals zero, so absolute equals atmospheric. Do you understand? And then, when you increase the pressure above atmospheric, then you have gauge, isn't it? Can you see that? From here to here. So this is now the gauge pressure. But the absolute will be from the reference zero, isn't it? That is including the atmospheric pressure, isn't it? So atmospheric plus gauge equals the absolute pressure. Are you following? Now, what about when you go down below the atmospheric pressure? Because gauge is zero here. So below the atmospheric, gauge is going to be negative, isn't it? Because it is zero on this reference line. So anything below it will be negative gauge. But what about vacuum? Vacuum will be positive. The vacuum pressure will be positive. Because the vacuum pressure is minus gauge pressure. Are you following? Yeah, I think that's it. So this is like the pictorial representation of the relationship between absolute atmospheric, gauge, and vacuum pressures. And all this is in REN 201. Right? Okay? So now, having reviewed all this, I think now we are done with pressures, isn't it? So that now, when I mention any type, when I mention pressure head, you wouldn't mistake it to mean piezometric head. And you wouldn't mistake the same to be hydraulic grade line, isn't it? And you wouldn't mistake it to be capillary pressure. All these are different, and we have already explained, isn't it? Okay? Oh, thank God. We are now through with the first presentation, which, like I said, was prepared to be delivered in the first lecture. But it took us about 4 lectures of about 6 hours altogether. Okay? These are the references used in formulating this presentation. You have this groundwater contamination. Unfortunately, I don't have the soft copy of this, but I have the hard copy. And then this one, also I have the hard copy, not soft. And then this one, also the hard copy. I don't have the soft copy. But probably, you remember I gave you the website for downloading ebooks, free ebooks. So you can check and see if you can find them, okay? If you do, please let me know also so that my e-library can be upgraded, okay? But these are very good references. Of course, with every presentation, I will write the references used in generating that presentation so that you can go and get those books, have them, go through to have wider explanation, to have more explanation and deeper understanding. Because no matter what here is just like to guide you here and there. And then the main work, you will have to take your time out and have those books. Although I have already given you links to some of the ebooks, which I will also be using. That is FETA. In the next presentation, I use most of the information is from FETA, and then probably groundwater contamination or other sources, which will also be given. Okay? Now, having concluded this presentation, I will post it on the WhatsApp group, which has been created. And I hope each one of you are part of this WhatsApp group. Is there anybody that is not part? Although I'm seeing a new face, or 2 new faces, probably. Or is it 3? This last 2, I think, this is the first day you are attending, right? Okay. So, if you are not part of the WhatsApp group, we have a WhatsApp group for the course, in which we post all relevant materials that have to do with the course. We have posted the syllabus, we have posted, that is the library e-resources, the databases and the password login details and the websites for free download of ebooks. And then we posted, and now that we are done with this presentation, I'll post it also in the group. So if you join late, it means you will not see previous posts. So make sure that either you ask any one of you to repost or to get it. Okay? And then, I think we move to the next one because I still have time. Yeah. Okay. Yeah, wetting and between non-wetting fluid and the wetting fluid. Yes. In the unsaturated zone, you have wetting fluid. Definitely, you have water. Yeah, it is only unsaturated because the void is not completely filled with water. So that's why it is unsaturated. But the saturated, the void is completely filled with water. So that's why it is called saturated. Okay? But all times in the unsaturated zone, you have moisture. It's just like in the atmosphere. Because part of the components of the atmosphere is about, I think, probably is it 0.003 that is what? Moisture. In addition to the other gases, oxygen, nitrogen, inert gases, and then you have moisture. Okay? Although this depends, it has spatial and temporal variation also, the moisture. Like here, this is tropics. In the tropics, we have high moisture because we have a lot of plants, we have a lot of surface water, evaporation is taking place, so humidity is high. In the desert, the Sahara Desert, in that area, the moisture is next to nothing. Very dry. The air is very dry. You have high sunlight, moisture getting to zero. So, moisture is component part of either the atmosphere or the soil. Okay? Yeah. Any other question? Because now we are done with the first part. The first part, if you have seen what we did, basically was to review the hydrologic cycle, and then the types of aquifers, and then the different zones in the groundwater, sorry, the subsurface, the different zone of the subsurface, beginning from the unsaturated zone, which is called the vadose zone, down to the capillary fringe, and then to the saturated zone, and the associated properties of each of these zones. Okay, so now we will start with the next presentation, which will now take us into, we are still on aquifers. We will now start talking about the properties of aquifers. We just explained about the classification, the types that we have. Now we'll look at the properties. What are the properties of these aquifers? Okay? Come and check what you have.